I'm going to try to explain instrumental variables, and that's a method we use in order to isolate the causal effect of one variable on another. And let's use an example. Let's say, to what extent will education influence your salary? Let's say it's university education, and maybe university education will increase your salary, but we want to know how much. And the basic problem we have is that we don't have all the information necessary. We suspect, for example, that IQ is important in terms of determining how much education you get, but it's also important in determining your salary, even if you didn't get any education. So there's a variable that is behind both of these variables, education and salary, and we don't have that information. So how can we then estimate the causal effect of education on salary? It turns out that if we have information about one variable that it affects education, let's call it Z so far. If we have information about some Z variable that affects education but does not affect the salary or the outcome directly, we can use that Z variable in order to isolate the effect of education on salary, even if we don't have information about IQ. And that's the beauty of this method. We don't need to worry so much about these variables that are so-called confounding variables here, because if we have one instrument, that's what they call the Z, then these variables will be taken care of basically. So let's try to find one such variable. One variable that could affect education but should not affect your salary directly might be the month when you were born. So why would that be, the birth month? Well, what if in the US system, when you have to quit school, and you're allowed to quit school when you're 16, but you're not allowed to quit school until you turn 16, actually turn 16, which means that people born in January, for example, they will not be allowed to quit school until they turn 16, but they all have to start school in June or July or August. So they start school at the same time with the people who are born, for example, in December. Now that means that there will be a difference. They all start school at the same time, even though they're born in January or in December, but they're allowed to quit school at different points in time because they will turn 16 at different points in time. So there will be a small correlation probably between the month when people are born and how much education they get. Like if they graduate high school and how many months or years of education they get before they graduate or do not graduate there. So if that is true, if you have such a variable where the month you're born actually affects education, but the month you're born should not affect salary directly, then we can use that to find the effect of education on salary. And that's the basic theory here. And it's a beautiful method if it works, because you don't have to worry about any of these variables that causes so many problems usually. So how does this work? Well, there are two steps. Step 1, step 2. And remember now we're trying to estimate a relationship. So say y is the salary you get, and you have a plus b, then you have a coefficient for education. And the problem is you can't just run this regression because you should have included, let's call this B1, B2, IQ. You should have included IQ, and there's a correlation between the education and IQ. So if you just run this part, you will get an error because this education part will pick up the effect of IQ. So you'll overestimate the effect of education if you don't have this IQ. So we need to do something. The first step is to estimate to what extent will actually the birth month affect education. So you estimate, instead of putting education in directly here, you first estimate the relationship between education and the instrument you have. So you run a regression, A plus B Z, and Z here was the month you were born. From this, you will get an estimate. You can predict how much education a person will have given the month they were born. So let's say that's an estimate from that education. So the first step is to take the relationship between the instrument and the treatment here and estimate that relationship. You can then predict the values of the treatment given the instrument. So you get a value for that for every single unit or individual. Now, in the second step, you just replace the variable you wanted to include, education, with the estimated education based on the instrument. So now you will estimate the following: ay is equal to a plus b, and now you're not using education but the estimated value education from the first step, and you're running that regression. And this regression, the coefficient you get here, the beta, will be the true effect, if all the assumptions are met, will be the true effect of education. So it's a two-step method. First, you estimate the relationship between the instrument and the treatment, and then you put the predicted value into the equation itself. Now, there are two assumptions that are needed for this to work. The first assumption is that there is no correlation between Z and the outcome itself. There should be no correlation between Z, the instrument, and Y, the outcome. The second assumption is that there should be a correlation between the instrument and the variable you're trying to, the treatment you're trying to estimate. Let's call it, in this case it was education, but let's just call it the treatment in general. It could be Z and D for treatment. So here education will be D. So there should be a correlation between the instrument and the treatment, but there should be no direct correlation between the instrument and the outcome. There will be an indirect correlation, of course, but that goes through the treatment. Now, the second assumption we can test for that. It's possible to test, is there a correlation between the month you were born and how much education you get, for example. That's fine. It is impossible to test for the first assumption. Like, is there a direct relationship between the instrument and outcome? We have to use theory, we have to try to make it plausible somehow, but you can't really test it. So that's a problem here with this method. Another problem is that if you look at these two assumptions, maybe they are weakly fulfilled. So maybe there's a small problem with a second assumption and a small problem with the first assumption. And maybe you think, it's a small problem with both assumptions, so it's going to be quite okay. No, it turns out that if there's a small problem with the second assumption here, so there is a correlation, a small, weak correlation only between Z and D, the treatment and the instrument. So maybe that's a weak correlation. And maybe there's some remaining correlation between the instrument and the outcome. In that case, the beta we will get, the estimate we will get for the causal effect, will be very wrong sometimes. It can be a high bias, a big bias. So that's another problem here. But if the assumptions are fulfilled, it is a beautiful method, because if you look at some of the other methods, we have to have lots of information in order to find the causal effect. We have to have IQ and all the other information, all the confounding variables. In this method with instrumental variables, we don't need that. But we do need quite strong assumptions, and that may be difficult to justify.